So we are starting chapter 5, which is all about probability, and we're starting with randomness. So we're going to talk about flipping a coin. When I flip a coin, what's the probability that I get heads? 50%. Okay, cool. So what we're going to do is we're going to flip a coin 20 times. How many heads should I get?
10.
Am I guaranteed to get 10?
Absolutely not.
Why not?
Because it's random.
It's random. Okay, so we have two kinds of probabilities. We have the short run and we have the long run. In the short run, we have a lot more variability. In the long run, it starts to even out. So this is when I flip a coin 20 times, and I'm counting the proportion of heads, okay? Over here, this is me flipping a coin 500 times. Notice that in the short run, in the beginning, it's very varied. But as I continue to flip it, it starts to level out, okay? That's just because of averaging numbers and all that kind of stuff. So here's the idea behind this graph. This is short run, more variability. Long run, probability levels out. So I want you guys to keep that in mind anytime we do any kind of a probability example. In the short run, you shouldn't be shocked if you don't get exactly what you think you should get.
I don't have like the papers.
Oh, yeah, I got it. So, like for example, we roll a die. Okay, we roll a die. What's the probability you're going to get a 6?
1/6.
1/6. If I roll a die 6 times, am I guaranteed to get a 6 one time?
You are not.
No. But if I roll a die 600 times, about how many 6s should I have gotten?
Around 100.
Around 100. Am I guaranteed to get 100?
No.
No. But it should be close to 100. If I roll a die 600 times and I only get 10 6s, what would we think? I've got something wrong with my die, okay? Like it's weighted in some way, okay? All right, cool. So, law of large numbers. That's kind of the idea behind the law of large numbers. So the law of large numbers says that if we repeat a chance process many times, we will approach the theoretical probability. Now, theoretical probability, what is that?
Probability in theory.
Yeah. It's just like, it's like what we think it should be, right? 1/6 for any side of a die. 1/2 for a coin flip, okay? So if we do something, the more and more we do it, the closer and closer we should get to that theoretical probability. That's the law of large numbers. Any questions about that? Easy enough. Most of that is pretty intuitive, but that's what it actually is. Okay. How do you interpret a probability? In statistics, we do interpret probabilities in the long run, in the many situation. Okay, so basically we do need to make sure we note this. Probability is between 0 and 1. That is 0 and 100%, basically, okay? How many of you have ever had a parent or a coach tell you to give 110%? Guess what? That is statistically impossible. You can only give as much as you have.
I'll tell them that next time.
That's right. Tell them that next time. No, don't do that. That would be a bad idea. All right, so, but in statistics, when you're doing probability, or you're talking about the chance of something, it does have to be between 0 and 1, if it's a decimal, or 0 and 100% if it's a percent. All right, so here's how we interpret probability. It is if we repeat process many, how many? Many. That's literally a thing, okay? If we repeat process many times, about that value will show up. Huh?
Your keyboard's unlocked. Are you sick?
Uh-uh. So here is an example. The probability of getting a sum of 7 when I roll 2 dice is 1 out of 6. Interpret this value. This is how it works statistically speaking. If we roll 2 dice many times, about 1/6 of the rolls will sum to 7. Whee! That is how you interpret a probability, statistically speaking. Notice I did not say that if I roll 2 dice 6 times, I'll get 1 sum of 7. No, not guaranteed. Okay? I use the word about, and I use the phrase many. That's how we interpret in statistics. Okay, let's talk about the real world. Do you guys eat breakfast?
No.
Wow, listen to that. It's scary. According to the Book of Odds website, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Explain what this means.
61%.
If we select many U.S. adults, about 61% will say they eat breakfast. Okay, so hopefully, like when you guys saw this question, you saw 0.61, like you kind of knew what it meant, but like now you know how to say it like statistically speaking. Okay, so there it is. Now, why would it be wrong of me to say that if I choose 100 U.S. adults, that exactly 61 of them would usually eat breakfast? Why would that be wrong?
Because it's random.
Very good. And what'd you say, Garrick? No. Who said something?
You said it's not guaranteed.
Very good. Probability is not guaranteed. Now, should it be close to 61 of them?
Yeah.
Sure, but I'm not going to be guaranteed 61, okay? So, probability is not guaranteed. Now, I have a question for you. If I know this data and I go out and I talk to 100 adults, could it be that 61 of them say that they eat breakfast?
Yes.
That's totally fine, and I would not be surprised at all. Would I be surprised if like 50 of them said that they eat breakfast?
No.
Maybe not. What if only 10 of them said that they eat breakfast?
Yes.
Now I'm probably starting to get surprised, okay? I want you to know that that's where all of this is heading, okay? If we know a probability and then we go out and we take a sample and we get something different, are we surprised or are we kind of like, it's just variability in the sample? That's where all of this is heading, okay? All right, let's look at some probabilities. Here we have 6 probabilities. We're going to match one of them to each of the following statements. Some of them can be used more than once, and some of them might not be used at all. And we might have more than one answer for each one. So here we go. Which one of these probabilities would mean that the outcome is impossible and it can never happen?
0.
That would be a 0. Can anybody give me an example of something that has a probability of 0?
Ryan getting a girlfriend.
So, I just want you guys to know that is now the second time I've heard that example today. Not Ryan specifically, but in my second period, it was someone who said, me getting a girlfriend. So that's now my personal mission, is to get that man a girlfriend. So it's fine. So if anyone's available, let me know. So other than poor Ryan not getting a girlfriend, give me another example of something that is statistically impossible.
Rolling a 7 on a 6-sided dice.
Beautiful. Rolling a 7 on a 6-sided die. I have a bucket of red and green marbles. What's the probability I pull out a blue one?
0.
There you go. Okay, so things like that. Okay? All right. What about the outcome is certain? It will occur on every trial.
1.
Give me an example of that. Danny being sarcastic. Sun coming up in the morning.
No, it's not.
When has it not happened, bro?
Many trials.
Oh, yay, Alaska. Okay, all right. Well, never mind. So that's off the table. Give me another one. We're looking for something that has a probability of 100%.
Every person that has breathed has breathed at least once.
Okay, everybody, the probability that you have taken a breath if you've been born alive.
Not 70%.
100% of babies have a lot of time.
Oh, okay.
There's probably some babies that haven't died.
How about this? If I flip a coin, what's the probability I'm going to get either heads or tails?
Almost one.
Well, you could
Almost
land on
one.
the side.
It never lands on the side, gentlemen.
Hey, what if it were in space?
I've seen it happen.
Yeah. All right, fine.
Almost one.
I quit. All right. The outcome is very unlikely, but it will occur once in a while in a long sequence of trials.
0.01.
Okay, 0.01. That is associated with what percent probability? There's a 1% chance of something happening. Okay. Now, do you guys think that any of those other probabilities that are given would match this definition?
No.
No? None of you think 0.3 is very unlikely? You do?
It's more unlikely than not.
It is more unlikely than not, but is it very unlikely?
No.
Good. Okay, very good. This outcome will occur more often than not. What does more often than not mean?
A little more.
More than 50%. So what would go here? Now, this is where the debate begins. Does 1 belong there? Does more often than not include 1?
Yes.
No.
In a literary sense, yes.
No, it does not.
It can't be more.
Because it's more often than not.
By definition,
So it's
it must
not
be.
So,
More often than not, still it can happen.
more often than not implies that not is a possibility. But when you have a probability of 1, is not a possibility?
No.
No. So 1 is not included. All right, cool. Myths about randomness. Okay, you guys, now listen, this is really hard to understand. We are about to write down lies. I know, right? We're going to write down myths about randomness. Things that are not true. Okay? So here we go. Random events do not have patterns. That is a lie. Can you flip a coin and get heads, heads, tails, heads, heads, tails, heads, heads, tails?
Yes.
And it still be considered random?
Yes.
Absolutely. So this is a myth, okay? So again, I want to make sure you understand. You just wrote down a myth. This is not something true, okay? These are myths about random variables. Okay. All events even out in the long run. Is that true? Obviously not, because we just wrote it down and I told you you're writing down lies. All events do not always even out, okay? It could be that you roll a die 600 times and you don't ever get, you don't get to 100 sixes, okay? That doesn't mean that in the next 600 that it's going to even out, okay? They're not guaranteed to even out. Even in the very beginning example, when we flipped a coin 500 times, it didn't get to exactly a half. So this is this whole myth of the law of averages. Have you guys ever heard like a sportscaster say, yeah, they've been on a really bad streak, so they're due a hit or whatever in baseball. Or, you know, they've missed so many of their baskets, so they're due to make one. What? No, like, it's not like the basket sits there and goes, well, Steph Curry has not made one in a little bit, so it's time for me to make sure that it goes in. No, it's not like the dice are like, this person's been rolling for a while, so it's time for me to give them a 6. No, these are inanimate objects that have no memory, okay? So nothing like that happens, okay? It's just all chance process every time. All right, cool. All right, so speaking of streaks, right? So this is kind of like the basketball example I was just talking about. Is there such a thing as a hot hand or a streak in basketball? I know you guys all believe in this, and I totally get it, and I know that there's a lot involved here, but hear me out on this example. Belief that runs must result from something other than just chance influences behavior. If a basketball player makes several consecutive shots, the fans and the teammates believe that she has a hot hand or is on a streak and is more likely to make the next shot, okay? So you see this all the time. Michael Jordan, he's having a great game, so get Michael Jordan the ball. He's going to score for us, right? Is that really a thing? So here we go. Several studies have shown that runs of baskets made or missed are no more frequent in basketball than would be expected if the result of each shot was unrelated to their previous shot. When you are shooting a basketball, the basketball and the basket doesn't know that you're on a hot streak, okay? So the idea here is that if a player is a 50% shooter, then every time they shoot the ball, they have a 50% chance of making it. But guys, is it unreasonable to think that they might make 10 in a row? No, because randomness can have a pattern, and it can happen repeatedly. But maybe in the next game, they miss 10 in a row. But their probability of making a shot is usually over an entire season. So if you are a 50% shooter, that was probably last season, and we're seeing what's happening now. Maybe you've made some improvements in the off season. And so maybe now, the next time we recalculate, you'll be a little better, okay? But just so you know, the idea is that you can make a bunch in a row and it still be considered a random chance event. No. All right. Law of averages. Belief in the phony law of averages can lead to serious consequences or unwanted children. A few years ago, an advice columnist published a letter from a distraught mother of 8 girls. She and her husband had planned to limit their family to 4 children, but they wanted to have at least one boy. When the first 4 children were all girls, they tried again and again and again. And after 7 straight girls, even the doctor assured them that the law of averages was in their favor 100 to 1. Unfortunately for this couple, having children is like tossing a coin. 8 girls in a row is highly unlikely, but once the 7th kid is born, the next kid is equally likely to be a girl or a boy, just like every other kid was. And for that couple, it was a girl. Again, 8 girls in a row. The law of averages is not a thing, okay? So be careful if you read something and it says, oh, well, this has happened so many times in a row, so it has to even out. No, it doesn't. It's not a thing, okay? Awesome. All right, let's look at an example. Tossing a coin. Which one of these is more probable? Heads, tails, heads, tails, tails, heads, or tails, 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 heads, heads, heads?
Either equally.
What?
Yeah.
Are you sure?
Yeah. Because you're still demanding a specific side each coin toss.
Equally likely.
That's what I said earlier.
Man, you guys are the only class that hasn't fallen for my trap today.
Just explain it.
I know, right? It's almost like you guys are like super in tune with what's going on. All right, now we're going to do this little activity. It's kind of fun. I want you guys to imagine. Don't pull out your phones and use Siri. Don't talk to me. But just imagine flipping a coin. What did you get? Write that, either an H or a T, underneath the number 1. Now imagine flipping it again. What did you get? Okay, here's what you're going to do. You are going to randomly flip a coin 50 times really fast. Go. Flipping a coin, imagining what you got. Just write down whether you're getting heads or tails each time. Flip a coin really fast. Here we go. Go, go, go. We're flipping a coin. We're writing down what we're getting. Heads, tails, heads, tails. What are we getting? We're just randomly flipping a coin. Would that be random? We're just randomly flipping a coin 50 times, writing down what we're getting. We're imagining doing this. We're not doing anything with our phones to tell us to flip a coin or anything like that. We're just randomly flipping a coin. It's super exciting. Who's having a great time? That's me. Let's go. Wasn't that hard? All right. A run. Anytime you go on a run of a probability event, that is the same thing happening in a row. So what I want you to do is look at your random flips. Count your longest run of the same outcome. It can be heads or tails, it doesn't matter. But how many in a row did you have consecutively? What was your longest run? All right, Elizabeth, what was yours? 4, 6, 4, 4, 3, 4, 4. Yours was 50, right? Yeah. There's always that kid right there. All right. 4, 6, 6, 5.
This was 4.
4, 5, 4, 4, 4. Danny?
Oh, 4.
4, 3, 7, 8. Andrew? 20. 3, 4. Oh, man. 4, 7.
The longest heads or tails in a row.
3, 3, 3, 3. Okay.
You know we're paying $2 because they said opening $10.
Oh, yeah, I do. Okay, so what do you guys notice here? What is the most common run in a random flip? Obviously, it's 4, right? You guys were all random, right? You weren't considering anything, right?
No.
Okay, all right. I'm going to give you guys an actual penny. Like a real one. Yeah, you can keep it if you'd like. And I want you to actually flip this penny 50 times. I'm not going to tell you how to flip a penny, but I am going to tell you a couple of pro tips. If you flip it on the desk, it's going to do that. So you might want to flip it on your paper, okay? That just helps keep it not running away, all right? Now, if you want to flip it, catch and turn, that's fine as long as you do that all of the 50 times. So however you do it the same all 50 times. And you're just going to write down if you get heads or tails. Make sense? Perfect. So now we're going to make a new dot plot. So tell me, how many did you get what was your longest run when you were actually flipping? 6. 5. Lindsay? 7. 5. 4. 6. Kimber? 7. Jackson?
5, no, 6.
9.
6.
Maddie?
4.
Again?
6. 4. 4.
Garrick?
8.
10? Nuh-uh. 9. Aaron?
Tails. Oh, wait, no, 8.
Andrew?
Right.
5.
7. 4. 7. How about back here? 8. 6. 5. 12. Actually?
Yep.
You guys, what happened here? Okay, why did you guys change your heads or tails when you were thinking about it in your brain?
Because we thought we wanted it.
Because you thought it wasn't random enough unless you flipped it. But look, actual random things happen more in a streak than you would think. Like people making baskets on a basketball team.